Daydream and Cardboard. We have two big ambitious goals today. The first one will be to build a VR scene. So we're going to be using the Google VR platform. So the Google VR platform, it supports both Daydream and Cardboard. It allows developers to target both platforms at once. And when you do that, it's basically an exercise in graceful degradation, right? On one end with Daydream, you're going to get a fancy remote, a high frame rate. And on the other end with Cardboard, you're going to get to look at things, and the frame rate is not that great. Our second ambitious goal is going to be to create a Tango app. Now you can think of Tango as an augmented reality platform. I think I'm going to get feedback at some point. Just note for the PA people, right? So yeah, Tango is an augmented reality platform, but technically it's a bit more than that. It lets a device understand where they are in the world and detect what is around them. And it does that by leveraging computer vision and specialty sensors on the specific device you're working with. So our application is going to use Tango's motion tracking, aerial learning, and depth perception APIs. We're going to see how to populate a real space with virtual objects. So what are we going to use to write our app today? Unity and Unreal are the go-to platforms for VR content creation for sure. You need to import 3D models, animate them, simulate physics, edit scenes, all that jazz. Unity and Unreal are really hard to beat. The problem there, though, is that with Unreal and Unity, they're game engines. And as an app developer, which this conference is all about, we want to access awesome APIs and libraries that are available on Android. With Unity and Unreal, you mostly lose access to all of this stuff. So with that in mind, today we're going to use Java and native Android tools. So OpenGL is the standard when doing native mobile development 3D. And it's actually getting better and better. So with each new version, OpenGL ES adds features that were only available on desktop OpenGL in the past. So this means that nowadays you can push the envelope in a big way and get awesome looking results. The issue is with OpenGL ES is that it's a pure graphics library. It's not going to import your 3D model. It's not going to animate them. It's not going to detect collisions. You're not going to get to simulate physics easily. You're going to have to do all that work on your own. So to top it all off, the OpenGL learning curve, which is the whole little joke here, is kind of pretty steep, and it's very unforgiving. So when you mess up, at best you're going to get a crash, a blank screen, and maybe a cryptic error message if you're lucky. So, you know, it's a pretty big time sink for most people starting out with it. So Rajawali is a library that can solve that. It's a lesser-known Android Java lib. It's built on top of OpenGL ES. It provides supports for building complex 3D scenes. You can load models from various 3D file formats, not all of them, but a good selection of them. It helps with animations, and it has a slew of other nice little features. It's built on top of OpenGL ES, so that means that you can actually still interact with OpenGL if you need to. And also it's open source. So there's a lot going for it. Okay, so we're going to start on our first ambitious goal, which is how to build a VR app. We do have a little problem here because Rajawali's VR support is for the original cardboard-only version of Google VR back in when it was in version 0.7. So with the introduction of Daydream, some breaking changes have come up. The good news is I have you covered, right? So a modified version of Rajawali's VR classes is available on the GitHub URL below. And also it's where you're going to find all the sample code for this presentation. All right, so now we're going to see how to build a VR app, the 10-minute edition. Right, I've mentioned that Rajawali is an abstraction layer on top of OpenGL, so I want to avoid a deep dive because that's where I usually see a lot of glazed eyes. But it's important to understand a few key concepts still. So with OpenGL and Android, your GL surface view is the view component you add to your layouts. You're going to need to assign this view a renderer of your own making. So this renderer is where you find all the OpenGL commands that draw to the screen. It's also where most of the complex setup code is going to live, usually. So another important concept that is still useful today is the GL render thread. So the role of that is to keep the 3D rendering fast and smooth. It's working much like the UI thread that we're all used to. So it does mean, though, that we need to be careful how we interact with the GL thread. We're going to want to avoid heavy work, just like the UI thread, of course. You're going to have to be very aware of thread safety. So when you're going to pass variables to your renderers or pass attributes and all that, you're going to have to make sure that these things happen on the right thread. Otherwise, you're going to run into concurrency issues. Right, so since you can't just change the renderer's state from the UI thread, classic OpenGL on Android would expose a method called queueEvent, which you would just give a root runnable to for that, for that purpose. So that runnable will execute on the GL thread. All right, so last diagram here. So here we see how Rajawali abstracts away OpenGL. The exact details are not really that important. The really important part is that you still have a surface view on hand, and you're going to assign a renderer to it. So that's very similar to what you would have done with OpenGL if you're used to that. All the 3D drawing code still lives in the renderer. It still executes on the GL render thread, so these things are still true here. And we're going to see that thanks to Rajawali, the renderer will actually be a lot easier to implement. So let's start implementing that renderer. So at the top here, you see sort of it's maybe a bit faded, but we're talking about the init scene method that you would have in the renderer in Rajawali. So the first thing we're going to do, we're going to set the background to blue, right? Easy. Then, before going further, we're going to need a light source. Light is a key component of 3D. It's usually where also things kind of get very complicated if you want to make very realistic-looking scenes. We're going to keep things very simple today. We're only going to create a directional light source, as you can see. We're going to place that light source at the coordinates 0, 10, and 0. If you're not familiar with like X, Y, Z and vector coordinates, this is going to be at top of the origin at 0, 0, 0, 10 units above it. So the light will be looking at the origin, so it's like shining directly down. You can see a convention here with Rajawali where you can point things at something and then say enable look at. That works for all sorts of things. You can even have models that you would say, I want this model to look at this item in the scene. So that's actually very practical when you want to place things in the world. So directional light acts like the sun. The angle between the light source and the surface normal lets us calculate how much light is going to bounce off that thing and how much light is going to reach your camera or your eye. Right? That's how you decide how bright the color is going to be. So using all that information, we're going to be able to light up objects in our scene, very much like the last picture I just added here. All right, so let's start rendering. Rajawali provides many model primitives that we can use. So if you want to play around in the sandbox, that makes it easier. Here we're only going to create a simple cube, right? Very simple stuff. We give it dimensions. Then for the light to actually light up something, we're going to need to assign a material to that object. So here we're going to be configuring our material to be red, and it's going to follow something called the Lambertian lighting model, which is basically what I've talked about, like the light bouncing off the surface of the object. It's just fancy language for saying color intensity. Right. So as it stands, our cube is very flat. We're going to need to move our camera in the space to see the effects of perspective and how we light our model. You can see it's actually pretty simple to orient cameras with Rajawali again. We just set the look at parameter. We set where the camera is, and we're going to have the camera pointing to the origin. So that's kind of nice, kind of easy. So what's next? Well, we're going to want to look at animations. So to animate an object with Rajawali, you can use one of the provided animators that we can see here on screen. In this instance, we rotate our object along an axis. So the axis is the vector that we pass in the method here. We also specify the total rotation in degrees, so 360. It's going to do a full turn. Then when we assign the animation to our cube, we want this full rotation to happen over 2 seconds, and we want to repeat that to infinity. So this what gives us our effect with the spinning cube forever there. So last step is to register that with the current scene, and all we need to do with an animation is basically call the play method. So all of this is still happening in the initialization phase of our rendering. We're not even really writing rendering code yet, and we get all of this basically for free. All right, so you might be wondering, how hard is it going to be to add VR to this little scene? So let's look at that. Most of the activity code for our VR sample is actually here. So we're going to be extending something called GVR activity, which is the baseline activity in the Google VR SDK. It's not a Rajawali thing. Then we're going to need a view widget as a display. So Raja VR View extends Google VR's GVR view. So you're going to find the modified Raja Wali code for the in the GitHub repo, like I mentioned before. So just take that and look at that. It provides all the hooks that you're going to need to get Raja Wali and Google VR to work together. And the benefit there is that we get to skip over all the nasty OpenGL stuff, right? So the last step here. So the last step here is you're going to pass your implementation of the renderer to the GVR view. Just simple assignments, basically. Like the GVR view itself goes into GVR activity, and your simple VR renderer here is the VR version of the code I just showed you for that red cube. So that's the last piece that's missing. I'm going to show you what's in there. And there's only two things that you need to change in your renderer, besides making it inherit the right type of renderer. So first, the camera arrangement is no longer relevant. Right? In our VR scene, the headset is the camera. The headset is set at the origin, 0, 0, 0, by default. So the SDK takes care of matching the camera orientation to the orientation of the headset. So second, since our cube was defaulting to the origin so far in our example, and our head is now at the origin, you're going to want to move the cube. Simple as that, and put it somewhere in space. And that's all we needed to get VR going here. Now you might be noticing I'm cheating because there's a skybox around this, but the skybox code you'll see in the GitHub repo is about 5 lines of code, so it's not that complicated. All right, so all of this together though, we have a working example, and if you ignore the usual Android boilerplate, I'm cheating a little bit, I counted 40 lines of code in the sample, and that's it. That's all thanks to Raja Wali, right? It isolates us from all the nasty OpenGL setup code. We don't need to worry too much about VBOs and all these fancy things at first anyway. And we can get going and start having experiments. That's fun. All right. So we've covered basics of how to render 3D objects and even do VR by the side. So we've seen how fast a 3D scene can become a VR experience. You just drop the Raja Wali scene into the VR Daydream wrapper and things are good. So a second ambitious goal now, Tango. Building a small Tango app. First off, you might be wondering, why would I make a Tango app to start with? The first Tango consumer device will be, hopefully eventually, the Lenovo Fab 2 Pro. This phone should have launched this summer. Now it should launch before the end of this year. It's hard to tell if it's going to be a successful device though, right? When you walk out of this session, should you be trying to make like a mass market app for Tango devices? Probably not, at least not today. For now, it's a very specialty device. So rule out ideas that depend on mass market adoption for now. Think about consultancy type scenarios. So things where you can provide the Tango devices to your actual users. Things like, indoor location, Tango is extremely good at that. So imagine a self-guided museum tour where you can add rich content to items in the exhibit, right? Like you can float around the T-Rex and you can see where it was dug up. Cool stuff. It's also great at mapping rooms. So you could use Tango to create precise 3D models of indoor spaces. So that's great for interior decoration or room monitoring scenarios. So this actually is a photo from a Montreal-based startup called Breather. So it's one of their spaces. They rent office spaces by the hour. So imagine creating a heat map of how people use one of these spaces. For them, that could be extremely valuable. You could adjust the design of the workspace based on hard metrics, like actually seeing what space in this, like where in the space people move, where they hang out the most. You could, redesign everything based on that. You could see why a room that rents a lot is different than a room that doesn't rent a lot. So that's like electronic feng shui. These ideas also apply to retail space as well. So you can think of small retailers. You could give them a much better idea of how their store layout is doing, like if it's efficient, if people look at all the merchandise. The same kind of insights that big retailers are getting without the big price tag of the consulting company that comes in and measures the whole space and looks at traffic. You could also imagine providing rich interactions on the spot. Walk up to an alley, maybe at the Home Depot or something, and know at a glance what part is in what drawer, how many are left, and if you need to reorder some. Then you could reorder that part on the spot. Just like look at the thing, see a little UI pop up, reorder. That could be very interesting. All right, so we have a lot of very nice ideas. So how do we make these come to life? Tango provides us with 3 core technologies. First, you have motion tracking. So that gives you the position and the orientation of the device in near real time. Like not industrial real time, but near real time. You get area learning, so it allows the device to recognize the space as it has seen it before. So this is a key component that enables indoor location. It also enables more precise motion tracking. So it allows the device to correct fly-by-wire errors that it might get if it's just relying on the sensors and the accelerometer data that it has. And finally, you're going to get depth perception. So by knowing what is in front of it, the device can let us map virtual objects onto real ones and vice versa. All right, so first is motion tracking. What do we track exactly? So the Tango APIs provides you with the position and orientation of a user's device in space in full 6 degrees of freedom. So that's called the device's pose. I'm struggling with saying pose instead of pause because in French it's kind of confusing. But anyway, you'll see me trip it up a few times during the presentation. So you can get Tango pose data in one of 2 ways. You can poll for it, but in our examples we're going to use callbacks, like this example right here. As the device moves through space, the callback can execute up to 100 times a second. Shown here is the full Tango pose data that you're going to get on every call. You notice that's a C-struct. But for now, there's like 2 important parts I'd like you to focus on. So the position of the device is going to be found in the translation array. You get a Java equivalent of that. It's a 3D vector, and it's in meters. So you're going to have to make a bit of a conversion. Sorry. And second, you have the orientation. So that one's a quaternion. Quaternion. So a quaternion, what exactly is a quaternion? It's the quotient of 2 vectors. So they fit in an array of 4 doubles. Instead of quaternions, if you wanted to define orientation, you could have specified a rotation along the x, the y, and the z axes. But you're going to run into a problem called gimbal lock with that. So that makes it mathematically harder to define an orientation. Quaternions are not subject to gimbal lock and are simpler to compose and use. So mathematically, they're a lot easier to use, if not easier to understand. But the big story here is that you don't need to worry about the math here. The APIs do all the heavy lifting for you. You just need to know why the quaternions are there and what they're good for. Right, so the Tango tablet is moving through space. How do we update its position in our virtual world? So we take the camera pose object, extract the position vector, which you see in orange, and the orientation quaternion is in blue. So you note that the orientation data needs a little bit of massaging before we pass it along to Rajawali. So the Tango array ordering is a bit different in this specific case. There's a few edge cases like that, but thankfully you have a little bit of source code to sort of look at to get these, so don't worry about them too much. Right, so there's a problem with motion tracking. When you start it, you'll know where the device is, but you'll only know that relative to your starting point. So when you turn on your software, your app, you're going to be at 0, 0, 0. And that doesn't help you one bit if you want to remember where you've been in previous sessions, right? You're putting down virtual objects. You want to, when you start up the app again, you want the device to know where it is in that space based not on where you started it, but where it recognizes itself in that space. So to be able to recognize an area, Tango has to learn about it first. So once an area is learned, the device will be able to remember that in future sessions. So one way to create an area definition file is by using the Tango Explorer application that we see here. It should be animating. Oh, wait, here's a small demo, right? Now it's animating, yes. So right now the device looks for and records the visual features of the corridor. So towards the end of the clip, we're going to see a green area localized toast. So that tells us that the Explorer understands where it is. You can then save a decent area definition file at that point. You know that the device kind of has understood enough about its environment to have a full picture of it. Yeah, so you might have noticed that this environment is actually noisy because I have colleagues walking around the corridor. That doesn't matter for Tango for the most part. You don't need to worry too much about that. It helps if the environment is not deadly noisy with a crowd of people moving about, but it's not the end of the world. You can still get some good ADF files out of that. Oh yeah, and an interesting point is that once you have an EDF file, you can actually copy that and give it to other devices, right? Otherwise, that would be kind of limiting if only one device knew where it was. So you can take these ADFs and just broadcast them to other apps. So it gets a little bit more interesting to look at ADF files in this video. So let's see how the device can relocalize itself. We're looking at the ADF inspector. So this app allows us to see how ADF files work in a very visual way. There's a lot going on here. So the blue pyramids, they represent saved poses or keyframes. The small green and orange cubes we see flashing there are landmarks. So landmarks are the visual features we talked about in previous slides. So that's what the device is recognizing in the images in this fisheye camera lens. Localization, that's what happens when the device recognizes its environments thanks to all of these features and thanks to the ADF. So once the device localizes, it lets it understand where it is relative to the file that was recorded earlier. So the more localization, like individual localizations with these features happen, the better the quality of your signal is, the quality of your calculated position. And that's the gauge you see on the right there. So what's interesting also with ADF files is you can add to them, right? So you can record one, say if you're one of those merchants I was talking about in some of the earlier possible use cases. If you go around and you notice with the ADF inspector they have a dead zone, you could restart the recording and just like scan that area again and walk around it and teach more, give more data to the model to sort of be able to extrapolate where you are better. All right, so you might be wondering how hard is it to manage the ADF files in your app? I've just shown you like Tango apps to do this, right? So first step, you need to get permission. This is kind of old school permission model type stuff. Tango has its own model for that, and I'm kind of curious to see what happens when we move out of development with KitKat devices into the modern world of Nougat, or Nougat, as everybody calls it. All right, so here we get permission. Then to turn on area learning, you're going to pass a flag when configuring the Tango session. When you're ready, you can save the ADF with one call to Tango. So it's fairly simple stuff. Now, how to load an ADF file this is how it works. I'm glossing over a lot of the lifecycle management code here, which is not that interesting, trust me. But that's the key core concepts with ADF files. You save them, you load them, you put your session into learning mode, and it will record. Right. So, thanks to motion tracking and area learning, we have a solid idea of where we are in the world. So to interact with that world, we're going to need to find out what is around us. So this is where depth perceptions API come in. They tell us the shape of the world around us. So Tango services provide depth data in form of something called a point cloud. So we can see one here. So this format gives us as many X, Y, Z coordinates as possible. There's a laser infrared blaster in front of the Tango devices, like the dev ones I have. And there's an infrared camera that allows it to sort of detect depth that way. So there's an important thing to consider, though, here. These coordinates that we're going to get in that data structure, they're all relative to the actual depth sensing camera itself, right? So imagine that the camera is at the origin of your world, at position 0, 0, 0, looking down the z-axis. The raw point coordinates we get don't take into account the actual position of the device, right? If we're like this, it's still going to tell me that point is straight ahead of you at a meter. So we're going to need to transform all these points to find out where they are in reality. We're going to come back to that later. Right, so in our app, we get the point data cloud, the point cloud data via callback, very much like the position data earlier. The onXYZIJ available method gets called every time new point cloud data is available. So we use a Tango support class called Tango Point Cloud Manager to store that info away. There's a lot of help going on with the Tango platform there. Like we get a lot of services. So at this point, we have the three big elements. We can track where our device is going, we can recognize the area we're in, and we see what's in front of us. So let's see how we can tie all that together to make something useful. Our goal is to add persistent virtual objects to the room. So to put these objects down, users will tap on the desired surface. In order for that to happen, we're going to need a video feed of some kind on screen. And that's non-trivial, but not necessarily that hard. So on the renderer side of things, this is what you need to display the video feed. So this is the Roger Wally code, very much like the sample code I was showing at the beginning with VR, the VR example. So a background quad, that's a flat rectangular surface that is going to take up the whole screen. So it's kind of a special surface because they're not actually 3D objects in our scene, even though we register them as such. They take up all the background. They're basically a static background that's going to take up the whole space. Even if you move in your 3D world, it's always going to be there and take up the whole screen. So that's actually perfect for showing a video stream. Next, we have to create a material that will show that video stream. So we bind the material to the quad, and then the next question becomes, where do we get the video data from? Actually, we're going to get it by exposing something. So we're exposing the Tango camera texture ID to the outside world, and we're going to see what the outside world is going to do with that. On the activity side, we're going to register a callback with Roger Wally. So that callback is going to be executed before each frame renders on screen. So we only need to connect to a given texture once, right? That's what this check is about. You connect to that texture like this. So this is the one call. You're giving Tango the ID that we just talked about, that texture ID. And it's going to autofill that with video data. So yeah, now you might be wondering, how come Tango knows about Roger Wally IDs? What's going on here? Well, I told you that OpenGL is under the hood. So actually, OpenGL works with these IDs. They're integers. OpenGL understands this, and Tango speaks to OpenGL and basically says, okay, so I have your texture ID. I'm going to register this video feed to you. So everything is under the hood. So this is how you do video. That's it. There we have it. Video. This is one of the other conference rooms. Yay. Video. Great. What's next? So we're going to want to add virtual objects to a location. So that's video of me in the Shopify corridors in Montreal. I'm actually tapping on walls via my tablet and surfaces to add this checkerboard pattern all over the place. So, oh yeah, well, there's a little anecdote about the checkerboard pattern. The first time I did this talk at Shopify, they were also live streaming it. So I don't know anybody, the AV's not here, but apparently checkerboard patterns can kill a live stream. This happens. Just as a side note, like I took care to have it like this, but if we're looking at it flat on, it could actually kill the live stream. True story. Anyway, so you might be wondering at this point, how much effort is going to be required to calculate a fitted plane from a simple tap on screen to 3D? Let's find that out. And fun fact, 150 kilos is actually 330 pounds. So that person is really, really strong. When a user taps on the screen, we're going to do a do-fit plane. We're going to call a do-fit plane method with a pair of touch coordinates, u and v. This is our x and y on screen. So we're also going to get a timestamp. And the timestamp is important here. We're going to get back to that in a second. All right, so the doFitPlane method, we're first going to ask the Cloud Point Manager for the latest point cloud. If you remember, our callback was only just passing that data along earlier. We were doing nothing with it, right? This is where we say to the manager, hey, give me your latest point cloud data. And I'm going to need a timestamp on that, by the way. So that's the extra wrinkle, too, here, is that not only are we dealing with timestamps, we're going to be dealing with two different cameras. So the first one is a depth camera, and the other one is a color camera. So that depth IR camera I was talking about, this is what's involved here, and the color camera is what we're getting our video feed from. So you're going to want to be able to move from the depth camera coordinate space, where your point cloud is, if you remember what I was talking about. We're going to want to move from that coordinate space to our color camera coordinate space. And if things were not complicated enough yet, we're going to have to deal with time. So the time we got the point cloud is not going to be the same as the one where we got our stream touch event. So those things are going to be different. So we need to map those out. So the good news, again, is that the Tango class will do all that hard math for us. We don't need to worry too much about it. It's baked into the SDK. Right. So at this point, we're going to use fit plane model near click method to get the fitted plane. So that represents the spot we've clicked on screen mapped to the real world. And we just basically need to pass the right values along. Like, I do think it's important to look at this code to understand what's going on. So when you eventually, hopefully, look at the sample code for this talk, you're going to understand where you're going, and you're going to have a mental model of where it is that things go. Anyway, so passing the right values along, our color to depth transform is here, the one we just showed in the previous slide. alongside the screen touch coordinates U and V, which we got earlier from the touch event. And then camera intrinsics here have to do with calibration and the camera's field of view, because that's also a thing that you need to take into account when you're doing AR. That comes from the Tango API itself, so again, it's not something you need to worry about too much. The last important critical thing is the data point cloud itself. That's the last parameter. So that's right there, X, Y, Z, I, J. All right, so there's one more transformation. Are you dizzy yet? Right. So the TLDR here is that there's a couple of extra transformation steps that are needed before we get back to Rajawali. And they're all ready to copy and paste in the GitHub repo. So don't sweat it, paste it. Snazzy. All right. So this is your main takeaway slide. All the hard work happens under the doFitPlane method in this sample code. So you take that resulting plane fit transform, you feed it to Rajawali, and you're done. So yeah, what does that look like? This is a demo of the sample code for the talk. So yeah, right, so you see the checkerboard pattern again, but I've added a few objects. So these are Rajawali primitives, like a cube and a sphere. It has its own little lighting model. So the demo code rotates through these three objects that you can place in your virtual space. And the area learning part of the demo code is actually not ready. It will be ready in the following few days. I had a few bugs with it today. I decided to concentrate on this nice presentation instead of working on code that you may or may not look at today. Right. Next up, it's worth noting how some extra operations actually are necessary to properly place virtual objects if you're going to do an actual app. So orientation actually works really great for plane fit transforms when you grab a plane from a wall, for example here. So that plane always points up, or at least it did in all my tests. The thing is though, if you click on the floor, you're not always going to get the orientation that you expect. So that's going to require extra finessing on your part to let the users, to give the users some sort of affordance to rotate objects exactly where they want to go. And this kind of makes sense because if you think how Tango works, right? You're clicking on the floor, it doesn't know which side is down if the plane is like this, right? So that's how things work there. Okay, so all these concepts can be pushed a bit further. So I wanted to close on this last little clip. This is a hack I'm working on to help measure and map out real spaces in the virtual world. So you take a real space, you sort of tag the walls, and it gives you like a sense of, you can make a model out of that you can then broadcast to VR. So the big idea for this, once it's going to be completed, is I can map a room and I can share the layout of that room with somebody wearing, say, cardboard or Daydream or what have you. So what we're seeing here is me tagging walls in a clockwise order with the app. And I'm going to let it run. But basically when you do that, that purple and yellow line that you see on the floor is like basically the intersection point between two planes. And this is actually pretty basic math, and it's inspired by some sample code from the Tango team itself. So you're going to find something very similar on the Tango side of things where you can tag walls. It's just a bit less fancy. It doesn't show you live what's going on, and at first you're not going to understand what's going on because the app will keep making these weird zigzaggy lines until you find out, oh yeah, I need to do this in a certain order. But anyway, so I think there's space to take a lot of the Tango sample code and turn it into actual actionable apps. And this is sort of one idea of 1,000 that you could be having. All right, so yeah, that's about it. So you can sort of see what's going on there. And small little note, you might actually notice that there's some drift at the base of the lines in some spots. And this is actually an area I had not learned. So that kind of drift would usually be corrected if you did the area learning step properly. All right. That's actually it for me. I'm early. I thought I would blow this session to hell with so I'm going to be ready for questions. And thank you very much for being here.